Okay, I thought I would run through some problems in 2.2 just so you can kind of get the hang of this pretty quickly. So what we're doing now is we're taking a derivative. We have defined the derivative using the limit process, and now we're going to look at some nice rules that are going to make our life so much easier. This is what Elizabeth has been waiting for. Um, so if I look at number 3, I have y equal 8. Okay, this is a function. I could have written it as f of x equal 8. Usually when we take a derivative, we show that by putting that little 1 mark there to say I took the derivative one time. The derivative of any constant is 0. That's the very first rule that you'll see there, Theorem 2.2 on page 107. So when you see something like that, it's very simple. It's just 0. The derivative of a constant is a 0. Okay. The next problem I see, let's look at, just kind of go through some of these here. Number 5, y equal x to the 6. Okay, this is why we love polynomial equations so much, and why we were trying to take things and reduce them to a polynomial equation. They are the easiest thing to integrate. We use something called the power rule, and what the power rule says is that when I take the derivative, I'm just going to put f prime of x instead of rewriting it, I take that exponent, I drop it out front, and then I subtract 1 from the exponent, so my derivative would be 6x to the 5th. Okay? Number 7. Number 7 says, flipping back over, at y equal 1 over x to the 7th. Now I can use the power rule here, but I'm going to rewrite this as y equal x to the negative 7th power. Ever wonder why we like negative exponents? Now you're going to know. I can drop that out front if I want to take the derivative. So let's say I'm going to do the derivative. That becomes negative 7 x, then I add 1 to... Okay, picking up again, sorry, I had a little interruption there with the door. You bring this negative 7, you drop it out front, so you're dropping the exponent out front as a constant, and then you add 1, let me see, no, you subtract 1 from your exponent. So you're subtracting 1 from your exponent each time. It gets confusing when you're doing negatives here. So negative 7 minus 1 would be a negative 8. That is my derivative. I could, again, if I want to know what the slope is at any point on a line, I could just plug my x in now, and that's how fast I could get it. I don't have to go through that long limit process because, people noticed these patterns in the past and noticed what always worked and came up with these rules to save you all that time, which is pretty cool. Thought we'd do some with some trig functions in it. So let's look at 19. 19 is pi halves sine theta minus cosine theta. So we got some special formulas for these trig functions. Okay, so if you're looking at your book, it's on page 112 where you see theorem 2.6 derivatives of sine and cosine functions. When I have something like this, I should have a y equal here. When I have something like this and I have two terms, I just integrate each term separately. That's one of those rules that's in this section, is that if you got more than one term, basically you can just take the derivative of each term and just kind of add them together. So if I have pi halves sine theta, pi halves is a constant. So when you have a constant term out front, you're not dropping down an exponent. The constant term basically stays. So when I take this derivative, I'll just put dy dx. There's all kinds of different ways to write the derivative. Here's one way that you'll see a lot. So the pi half stays, but if you look on page 112, the derivative of sine theta is cosine theta. Okay? Now I got a subtraction sign, and I'm going to think, well, what's the derivative of cosine theta? The derivative of cosine theta would be negative sine theta. It's also that same theorem. They give you both the derivatives of sine and cosine there. So the derivative of sine is cosine. The derivative of cosine is a negative sine. So we just need to clean this up now. That's pi halves cosine theta, and then a minus, minus a negative makes positive, plus sine theta. That's my derivative. I could write it, also as f prime of x. It's just these are the two ways I like writing best, because some of the other stuff just takes too long to do. So I like those. Let's pick a couple other things. So like 23, maybe you've got you got y equal 1 over x minus 3 sine x. Oh my goodness. So I went and did this, and I forgot to hit the record button, so I'm just going to talk back through it. On 23, here's your function. What I did was I rewrote this term right here as x to the minus 1. And the reason I did that is that now I can use the power property here. And and I just copy down the minus 3 sine x. So when you use that the power property, you drop the negative 1 out front. It becomes your constant. If there's anything else out front, you would have multiplied it. There just wasn't anything but the invisible 1. And then you write your x down, and then you subtract 1 from your exponent. So negative 1 minus 1 will be negative 2. And then I copy down my minus 3. The constant stays. When I take the derivative of sine, it's cosine, so I write that down. And all I did in that last step where I circled everything was that I rewrote negative 1 times x to the minus 2. We always try to write things without negative exponents when we give our answer. It's just that it's more convenient to work with the negative exponents in. It just works out so much easier that way for us to do this. So if you notice, what we're doing is we're just rewriting little parts of a function here to make it easier to take the derivative of. Okay, I thought I would do 37 just so we could have a discussion about, how do I think about this? Sometimes just putting thetas in there might mess somebody up, okay? Remember, if something messes you up, you could always think of this as f of x is equal to 4 sine x minus x. And that might help you do this. Just sometimes it's just something visual like that can help. And then at the end, you could put your thetas back in for your x's. That's what I'll do here, just to kind of provide an example. First of all, this is the function, but they also want us to find the slope of the graph of the function at the given point. Well, the point they're giving us is 0, 0. So after I find the derivative, that's what I'll do, is find the derivative next. After I do that and I get my derivative equation, I will plug in x is 0 into it, or theta is 0 in this case, and I will be able to tell you the slope at that point. So I could just, honestly, I don't know that I'm even going to have to switch back to theta here. Alright, so the derivative of 4 sine x would be 4 cosine x, and the derivative of minus x, if you have an x to the first power, let's think about how this would work. You drop your 1 out front, okay, so it would be minus 1. And then you would subtract 1 from your exponent. 1 minus 1 is 0, and x to the 0 power is just 1, okay? So you end up with 1. A lot of times we just say if you're taking the derivative of a linear term, we could call x a linear term. If I take the derivative of a linear term, it's just what was the constant out front. Well, it was a minus 1, so you'd have, the lazy math guy doesn't write the 1. We could write it in. Now I've got my derivative here. If I were being really careful, I would say that's really 4 cosine theta minus 1, because remember, I did that little switcheroo thing with the x's and the thetas just to kind of make it easier for my brain to grasp how to deal with it. You may not need to do that. I'm just giving tips for people who do need to do that. A lot of people are so visual that just changing one little thing like that will make the problem so much simpler. All right, so if I want to know this is the derivative equation, but it's not the derivative at the point. I have to find the derivative at the point. Let's say, okay, that's 4 cosine of 0 radians, 0 degrees, all the same thing, minus 1. So if you think about your little unit circle, 0 degrees would be right there on the unit circle. It has an x value of 1 and a y value of 0. And if you remember, on the unit circle, that x value is your cosine value of that angle. So that's going to be 4 times 1 there, minus 1, which would be 4 minus 1, which is 3. So the derivative at that point is just 3. This is so much easier than what we were doing in previous sections. So it's kind of like you work through a lot of harder stuff, and then you get to these rules, and it makes it so much easier. The harder stuff are the concepts, though. It's how did we come up with this? It's just some formula I can just do? Yeah, you can train a monkey to do calculus, but what you can't do is train a monkey probably to think through how you would derive those formulas and get them and what they mean and why they work. And so what we're trying to do is get to understanding, because if you're going to use this stuff, you're probably going to be using real-life applications, and you're going to need to understand that limiting process is occurring in any application you do. So that is your slope that at a point. That is your derivative. If you're looking for, what is a rate at a certain spot, maybe if you're a car, you're engineering something on cars and transmissions or engines or something at a certain speed, you need to know a certain speed. It is under certain conditions. That would be a derivative because it is a rate of change. It is a slope. It is a derivative. Okay.